Allora, buon pomeriggio a tutti. Abbiamo il piacere di avere con noi il professor Satish Singh dell'IPGPP, Institut Physique di Globe di Parigi, dove ha preso servizio nel 1999. La sua carriera è proprio uno scienziato del mondo, perché viene dall'India, ha fatto parte dei suoi studi anche in Canada, a Cambridge, oltre che a Parigi. Ha girato con rilievi oceanografici un po' in tutto il mondo, ha partecipato a ricerche sismologiche con OBS in vari oceani, in particolare ovviamente nell'Atlantico e nell'Oceano Indiano, e come vedete anche dalla prima immagine ha avuto un finanziamento ERC, è fellow dell'American Geophysical Union, e viene da una cittadina che si chiama Varanasi in India. Io pensavo che Roma fosse la città che avesse più chiese al mondo, 900, in realtà la sua città ne ha 2000 templi. E tra l'altro, considerato che qui abbiamo anche una macchina ERC che si chiama Shiva, e il Golden Temple di Varanasi è proprio dedicato al dio Shiva. E quindi ricordo solamente che il professor Satish è incredibilmente attivo, ha appena pubblicato 2 articoli recentemente su Nature Geosciences e anche su Science Advances, in particolare appunto sulla natura della crosta oceanica tramite analisi sismologica e sullo studio del limite litosfera-asthenosfera nell'Oceano Atlantico. Grazie, Satish, please, go ahead. Welcome.
Excuse me. Thank you very much, Claudio, for the invitation and hosting me here. And it's great to see. I heard so much about INGV. I came once, maybe 15 years ago now. But I'm glad to be here and see the exciting science going on here. I was at OGS last few days. I saw the other side, which is the marine side. So here it is really solid in every sense of the word, which is solid earth. Anyway, what I'm going to talk today is the work I've been doing over the last few years about the lithosphere-asthenosphere boundary, as you will see where I come from and get some idea. And it has been challenged, as you will see. Before I start, I would like to acknowledge all my students who did all the hard work. All I did is supervise them. So I will go through the whole thing and then I'll discuss the results. Okay, so basically, as you know, the plate tectonics has been the key of our past and future. And the plate tectonics is based on different plates and are bounded by plate boundaries. Plate boundaries are defined mainly by earthquakes. You will see them going all over the plate. And 3 of them we know very well. Oceanic spreading centers, where the 2 plates move apart, and the mantle upwells and oceanic crust is formed. At the other side of the boundary, which is the subduction zone, where the plate subducts and disappears in the mantle. The third type of boundary is the Seismic boundary, where 2 plates move apart. Fourth boundary, which we tend to ignore, is the base of the lithosphere, and which is the most prevalent boundary on the planet. It has to be everywhere. But unfortunately, there are no earthquakes at this boundary. So only way to do image and find out where it is to do some imaging. So I'll talk about that boundary. the best way to find this boundary has been using surface wave studies, using seismological methods. Surface wave provides, this is a 1D velocity model created by IPG group. First one is S wave velocity. As you will see, the S wave velocity decreases with depth. Do you have a pointer? No, no worries. So as you will see that velocity decreases with depth, and sometimes the gradient of this velocity is used to define base of the lithosphere. The second observation is anisotropy. Radial anisotropy changes at the base of the lithosphere because of the motion. And that sometimes has been used to define the base of the lithosphere. Third one is azimuthal anisotropy.
Sorry, Satish, you can use the mouse to.
Oh, yeah, okay. Yeah. So, and on a global scale, that was 1D. This is the work done by group in Cambridge, Creek Bisley group, where you could see that you can color. The beauty of our tomography is that we can produce a nice colorful images. Here is the velocity as a function of A's. As you will see near the ridge axis, near the 0 A's, you will have and it deepens with A's, and you can define a constant velocity contour to define the base of the lithosphere. The problem with this approach is the vertical resolution is on the scale of 20 to 30 kilometer, and here they had done the smoothing on the 800 kilometers. As you will see, things are not as simple as that. This is again two different results coming out of surface wave and anisotropy. On the top figure, you have the velocity as a function of A's, and the dashed lines are the isotherm, which is that provides the possible thermal structure or temperature as a function of A's. You will see that the base of the lithosphere deepens with A's, whereas based on the anisotropy, which is radial anisotropy, it is suggested to be at constant depth of about 70 to 80 kilometers. And so there have been two hypotheses. One is that it's a constant depth. One is where it's better. Obviously, when you start learning about the plate tectonics, you learn about not of velocities, but plates where you have mechanical boundary. The top boundary is mechanical boundary, which moves over a more ductile boundary. And the boundary between the two is defined as a LAB. If you are doing mantle convection, you will be looking at the thermal boundary, where you have a conductive lift at the top and adiabatic below, and the transition will be your lithosphere boundary. And I discussed those two anisotropy. And obviously, if you do anomalies, you will get the conductivity, and you will have a higher conductivity asthenosphere. So these are the different methods which are used to define the LAB. The revolution at that time, as we will discuss, resolution was 30 to 40 kilometers. Revolution came using receiver function. I am sure you all know what a receiver functions are. This is PTS converted waves, which allows us to define the boundary much sharper. What you are seeing here is this is the result from a Kawakasu in Japan, top of the subducting plate, which is the oceanic moho, and there is a negative polarity energy, which is, they call it base of the lithosphere. And they had one seismometers in the middle of ocean, and they tried to connect. The problem with receiver functions, the results are a bit more resolution on the scale of 10 to 15 kilometer, but it's patchy because you need a reflections coming out of a particular place. And then I go back to the Gutenberg. Gutenberg was the first one to identify there's a low velocity below the lithosphere. And he saw a low velocity zone based on the shadow zone. And that was in 1923 and 1948. And our friends, some of the seismologists, And they thought that this reflection interface at about the same depth. And they say that these two discontinuities are the same, Gutenberg as well as G-discontinuity and lithosphere boundary. So there has been two hypotheses which has been connected with the lithosphere-asthenosphere boundary. There have been two main competing models which will define the base of the lithosphere. One was produced by our friends at Karato from Yale, where he said that lithosphere boundary corresponds to the presence of high amount of water at about 70 kilometer depth. That will produce a gabbroic layer at about 70 kilometer. And in that case, the base of the lithosphere will be a constant depth. On the other hand, seismic results suggest that it varies 1/8, and there is presence of partial melt underneath the base of the lithosphere. So there have been two recent competing models of the lithosphere boundary. Based on the conductivity measurements, some of our colleagues from Scripps and Lamont, they found a high conductivity layer below the lithosphere, and this layer is about 25 kilometers thick. They suggested that is partially a channel rather than just a boundary. So the concept of channel started in 2013. So just to summarize what we knew when I came in the business, surface waves was most commonly used, but has a very low resolution. Resistivity, conductivity has a similar resolution. Receiver function was very much better resolution, about plus minus 10 kilometer, but only point observation. And that's where I come in. I use seismic reflection techniques, where my vertical resolution goes from 10 kilometers to 500 meters to a kilometer. And laterally is about kilometer to 4 or 5 kilometers, depending upon the depth. And the advantage of this approach that if it works, we can image continuously from over 0 to 100 million years. And you can see why I'm thinking, Carlos, when I think about that, the oceanic lithospheres are easy to work on. However, when I wrote the proposal, got the funding, and someone published a paper, Tim Stern, they did some survey in New Zealand on land using about 500 kilograms of dynamite. I don't know how they managed to do it. Over all lithosphere of subducting, they find a thin two reflections. And you could see these reflections. And in fact, you can't see it. They are very, very weak. But they managed to identify it. And they say that there is a two reflections, top and bottom. And there's a channel of about 10 kilometers thick, where the velocity decreases by 8%. But again, it is a very limited observation at only one age, 120 million years. And in the subduction zone, as you know, subduction zone, things changes because of the subduction processes. I've been doing imaging in the oceanic lithosphere using seismic technique. The main problem in imaging lithosphere in oceanic domain is the seafloor, which could be very rough. The worst is the water bottom multiples. Multiple energy goes up and down. And this is, for example, I did the survey offshore Sumatra, and this is the multiple from the seafloor. I could image the deepening reflector here down to 45 kilometers. That gave me the confidence that I can go deeper and image this technique. And but the lab will be flat, nearly flat, because it will not dip such a strong dip. So we need to be more creative and thinking. Then I need a low frequency. So lower than, because I want to go down to 100 kilometers. So I talked to a company called Schlumberger, who has been in seismic survey. That year, they had developed a new streamer, and I will discuss briefly that. This is very fundamental. Normally, when we have a seismic survey, we have a vessel towing a source, big source, and we have a streamer where we put mainly a hydrophone, a cable, 12 kilometer of cable. Since the energy goes down and comes back, it will be recorded twice. Once energy is coming here, and once reflected from the seafloor. And that in seismic jargon called ghost. And this will have a negative, this will be a positive contrast, and this will be negative of that because seafloor reflection coefficient is -1. And if in the frequency domain, this translates to a notch at about certain hertz. So you lose a lot of low frequency here. So the black here curve corresponds to the same signal in the frequency domain. However, if you are clever enough to put a geophone at the same location, and that's what they did, the reflection coefficient from the seafloor recorded by the geophone will be positive. It's very simple. Now I have two instruments, one positive, one negative. I add them together and I cancel the effect of the ghost. So basically, the response of the geophone will be red one with a notch slightly shifted with a 0 frequency. Once I combine them, I get a very broadband response and low frequency signal because I want to go deeper. So that was the idea I developed. I went to the company and they funded most of it, and that was Schlumberger. They provide their technology. I use a 12-kilometer multi-sensor. I had 4 components. Normally, you go with 1 component. You are seismologist, a lot of you. 4-component streamer. First time you are using in academic world. Very big source. We did not have earthquakes, but 10,000 cubic inch source. Acquired about 2,700 kilometers of the data set. Recorded down to 30 seconds to a travel time means down to about 100 kilometers. And did the survey from 0 to 75 million years continuously. My sampling is every 75 meters. And receiver spacing is 3.125 meters. So my sampling is very, very fine. So I will discuss to you 2 results. One from this area here across St. Paul fracture zone in the equatorial Atlantic Ocean, starting from the ridge axis all the way to 75 million years. This dog leg is unfortunately due to the EZ claim of the country. When we were trying to do the survey, we learned that country have claimed 350 miles instead of 200 miles. So we have to move around the profile in the real time. Anyways, we managed to acquire the data set. So this is the profile I'm showing you across St. Paul fracture zone in the equatorial Atlantic, where the age contrast across the fracture zone is from 40 million on this side to 70 million on the other side. And which means that I'm looking at the change in the lab if there's a difference. So that was the first time we did. This is the seismic reflection profile. You don't see much, but let me take you the tour. This is your sea floor and the basement. And you see a small reflection here, which is the moho, but weak. And this is your St. Paul fracture zone. However, if you look at carefully, I think you will see a energy here coming down. And that's the one reflection, and we see a second reflection. And that's reinterpreted, as you will discuss, top of the base of the lithosphere or lab channel, and this is the base of that. We published this paper a couple of years ago in Nature Geo. But the problem here is that I have 2 ages, only 40 and 70. I can't make a big, we did make a big story, because every time you publish a paper in Nature Geoscience, you make a big story. But you realize that I have only 2 ages. I needed a continuous seismic image. Yeah, I will discuss that briefly here. Some people argue that this is a multiple, but it is not a multiple. We got the polarity of the top reflex is primarily negative, and the bottom one primarily positive. But I will discuss that later, that I think it could be negative, as you will see in the next talk. The velocity contrast, we estimated using some methods. We find that you need about 8% decrease in velocity at both interfaces to produce that reflection. We can convert into depth using some simple model. This is the same profile with here is the distance along the profile. And this is here we are 40 million years. And you can see the top reflection corresponds to about 72 kilometers. It depends across the fracture zone to about 88 kilometers. And the lower reflection started at 88 kilometers, goes down to about 100 kilometers. The interesting bit, as you expected, that we discovered that there is a small steps on the base of that reflector. That corresponds to the small changes at the fracture zone age. So basically, it's very age dependent, even though we had a limited information. What else I want to say here? The most important result came out. The top reflection corresponds to about 1260 degree isotherm, and the bottom one about 1360. And we said that that reflection corresponds to the base of the lithosphere, and the bottom one corresponds to the base of the channel. But as I said, we have only 2 ages. We need more information. This is the profile we acquired from 2 million years to 5 million years on this side. We have combined the whole profile together. I'm afraid the image is not as nice as I expected it to be, or on my screen or published paper. You could look at it. Anyway, this is the sea floor. You can see the age deepens with age. And if you are careful, you will see a reflection here. And you can follow that reflection all the way up to here. And I will discuss that. It goes up and continues further up. You have a second reflection at about 27 seconds two-way travel time, and you can follow all the way to about 1000. This profile is about 1400 kilometers. So it's a very large profile. As you will notice here that we had no data set here, simply because here I was recording 30 seconds, shooting at every 75 meters. Here I decreased to 20 seconds. And this comes to preconceived idea. So once I had preconceived idea, which was wrong, I reduced my time because I'm close to this axis. The lab will be thinner. Unfortunately, I was wrong. So one has to be honest about the limits of our preconceived idea. Anyway, so this was the image which just came out last week. You will see it if you want to. I'll discuss the results from this one. The velocity contrast along this one. Here we have about 224,000 data points for the top reflection, and here about 112,000 data points. We try to get this global estimate, and there's a velocity contrast globally is about 5% for both 2 reflections. Polarity, looking at you visually, we get positive, negative, but we decide to have proper statistics. So we put all the data together. The top figure on all the data set for the red one is for the upper reflection, and the green one for the bottom. And you can see the probability of being negative is higher, more than 50% for the both cases, for the both top and bottom. And that gives us the idea of Gutenberg discontinuity. Both reflections have a decrease in velocity. In other words, the top one could be the lithosphere boundary, and bottom could be Gutenberg discontinuity. So this is the combined results from all published work on the lab with the function of age. The triangles are global estimate done by all over different people, and you can see that they are all over the place. So you can't trust any. There's no pattern. The results, these 2 ones are based on monotelluric and surface wave. This suggests that lab in this range is at constant depth of about 40 kilometers, which cannot be the case. It's a problem of resolution. So if you are looking at the surface wave, the lower one, this is I showed you the anisotropy determined by our colleagues in IPG, and that tells you there's something at about 70 to 80 kilometers. Our results is in red, which is for the top reflections, and for the bottom reflections, that one. So you will see, and these are the isotherms depending upon which model you use. The top one corresponds to about 1125 degree isotherm, and the bottom one is about 1250 degree isotherm. And you can see that it follows mainly the plate cooling model, and I will discuss this part of the study a bit later. However, this reflection, which is the lower reflection, remained constant for all the ages, starting from 27 million all the way to about 58 million years. So now we have a depth range, and we can talk about our age range, talk about the variations in that. So just to conclude, we have also imaged two reflections, both likely to be due to a decrease in velocity of about 5 to 6%. Upper reflection is nearly flat. I did not mention that for about 5 million years, and then very steep change in the dip of this reflection, and then it follows 1250 degree isotherm up to here, and it changes here, which I will discuss in a minute. What else I want to say? The lower reflection remains at the constant depth for the whole depth range. So what are the causes of the lab? There are two main, I have discussed that, grain boundary sliding and melt. The disadvantage of grain boundary sliding is that it only affects the shear wave, not the P wave. The image I have produced is the P wave image. So I require a P wave velocity contrast, not a shear wave velocity contrast. So that is not valid for our case. So the only thing we are left with is the presence of melt. So we can go and compute the amount of melt required using the effective median theory, using different approximations, which we developed a long time ago. We find that we need about 1.1% of melt at the base of the lithosphere in a form of a ellipsoids, which will decrease the velocity. It will also create the anisotropy, and hence can explain the anisotropy we observed below the lab. And of course, depending upon the type of the inclusion, you will need a much larger amount of melt if you think of its spherical inclusion, which is very rare. We have a problem. Our temperature is 1250 degrees centigrade. Normally, the melting starts at much higher temperature. The solidus is much higher at 1200, 1410 degrees is the normal temperature for melting. In order for the melting to occur, we need some volatiles. There are two volatiles. One are the CO2, one is the water. And here we estimate using water, and I will show you the results about the CO2 could play the role. We estimate about 122 million part per million of water at 58 kilometers, about 322 will produce the melt at about 1250 degrees centigrade. And that was our kind of seismic results. This is the work done by Oxford group, Richard Katz. Here is the melting at the ridge axis in the presence of zero volatile content. And here is the melting due to the 200 ppm of the water in this case. What is happening is that as the water content increases, the melt gets trapped. Instead of going up beneath the ridge axis, melt goes away from the ridge axis and it gets trapped below the lab, and melt will be present below the lab. So basically, our suggestion is that this model is approximately valid, and all these are due to the presence of volatiles and the melt. I said that you will see that my lab here changes from about 67 kilometers down to about 50 kilometers across a boundary here, because we had to change the line here. And you will see a small change in the A's, and that is a second order discontinuity. So from here to here, you will see the changes happening. And here, this one corresponds to an isotherm of about 1125 degrees. So supposed to be much colder. But it means that I need a lot of melt. The second possibility is that there is a thermal anomaly which has uplifted the lab. So the age contrast here between the other thing I should like to mention here is that there are two events happened in the past. St. Helena plume was there about 80 million years ago. And there is a Cameroon volcanic line which passes through not very far from our study area. So basically, we have two effects of thermal anomaly. One is from the past, one is from the present. The age variation between the St. Helena and our study area is about 20 million years. So basically, these two anomalies could produce shallowing of the lab. So what we did that we tried to cross-correlate the two ages, 27 to 40 million years and 49 to 75 million years. And we saw that maximum cross-correlation occurs about 20 million years, which is the age difference between the passage of the plume and the age of the lithosphere. So basically, the part of the anomaly could be due to the rejuvenated at the time of the passage of the plume. The second thing we notice, which could be for both, this is the seafloor bathymetry, a basement, red one, along the whole profile. You will see that the conventional subsidence model follows very well up to about here. And there is a shallowing of the basement at certain age in this area. It means that the basement has uplifted by a certain amount, about 500 meters. We can compute the whole thing. And to increase that by about 500, 600 meters, I need a temperature anomaly of about 120 to 30 million years, 30 degrees. So it basically corresponds to the same thing. And so basically what it tells us that there are two possibilities that this is the same thing with the hotter mantle. So if the mantle is hotter due to the presence of Cameroon plume by 160 degrees, then my reflection will correspond to the shallowing of the lab. So in other words, this is the sketch we prepare, the whole thing, that this shallowing of the lab is due to rejuvenated lithosphere, which is either caused by the presence of passage of the St. Helena plume or mantle anomaly coming due to the Cameroon plume. So there are two possibilities we could not distinguish because we don't have. And that comes back to the intraplate volcanism. So if you have a thermal anomaly or mantle anomaly, you will have a heterogeneity in the lithosphere and seamounts on the surface, which we see all over this place here. Then take the results which is deeper. So as I said, colleagues had been using the lab as a Gutenberg discontinuity or as a lab, and this is the model produced by Caroline Beckheim. She suggested that this could be a progen in boundary linked to the melting at the ridge axis, which is dry melting at the top and the wet melting at the below. This was work done by Marks et al. In 2021. They did compute the thermal strain effect due to the wet melting, dry melting at the top and wet melting below, and they could see there's a boundary developing. Could it produce a reflection? We do not know. So in other words, the second reflection here could be the G-discontinuity, which has been observed by the colleagues as from the anisotropy, where you have a hydrated mantle, dehydrated mantle above with a wet mantle below, and it gets frozen in and it stays on. At around certain age, when you have a thermal anomaly, it kind of remelts the whole thing and destroys the G-discontinuity. And this results explains the two observations. What about with younger lithosphere? And this is, we published this paper a couple of years ago, where we analyzed the data set from the John the Puka plate, very young age, about 0.5 to 2.6 million years. And the data were collected by our German colleagues in 1996. And when I was with them on the boat, I saw this data set. I said, look, guys, this could be the reflection we are hunting for. You can see these wide-angle reflections. So we were able to analyze this data and migrate it. We found there were two reflections, one at about 11 kilometer and second one at 14 kilometer. And they extend quite widely, either 25 kilometer and over a wide depth range. And that poses a problem. Initially, we thought that's the base of the lithosphere. And then we also computed the reflection coefficient. We find that velocity contrast of about 7% is required to explain that reflection. So we proposed two models, that was a couple of years ago. One was that this corresponds to the top of the lab, which is flat. Other one is that the lab is deeper, and these are the frozen in gabbroic cell in the lithosphere. And here is a model produced by Richard Katz, which we saw earlier. This is with age or distance. And once you move away from here, you'll see these gabbroic cells being frozen in. And we image them using our seismic images. So what we are discussing, Paolo, earlier, that because of this process, you could get some of the material from below the ridge axis get frozen in and become part of the lithosphere. So that's very exciting results coming out. So the next question you could ask, what happens beneath transform faults? So this paper is under review at the moment in Nature Geoscience. It will come out in a month or so. Been accepted. So we did some survey, reflection survey along Roman's fracture zone here, and using ocean bottom seismometers. And we were lucky to record reflection arrival up to about 700 kilometers. This is 560 to 700 kilometers. So this is the first time we could record such a large distance. We did the tomography and the velocity, and what we found that there's a low velocity extending from the crust all the way to about 60 kilometers. We found there is a velocity change in the gradient here, changes in the upper part and the second layer and the third layer. I'm not going to discuss what happens in the first two layers. I'm going to focus in the last layer. So our conclusion is that the upper one part is mainly serpentinite peridotite. This one is melanite. And because we have water going down up to about 30 to 40 kilometers, there is a melting going on the below the transform fault because of the water going down. And you could, first of all, have a melt, which is water-induced melt, and shallow the lithosphere-asthenosphere boundary. So instead of deepening it below the transform faults, you are shallowing it. It's exciting results. What about the presence of CO2? Means we talked about water. CO2 could play an important role in the whole process. This I put in because we talked today. So this is the results which we are about to submit soon on this. We acquired microseismicity study a couple of years ago along this Romanche transform ridge intersection. This is your ridge axis. I'm not going to go in the detail. There are two non-transform faults here, this one and that one, and I'll focus, and this is the ridge segment. So you'll see a lot of seismicity here and here, and I will try to discuss the results in the light of CO2. What we find is that below the ridge axis, which is supposed to be hotter, there is a strong seismicity between 10 to 20 kilometer depth. Below the transform, below the non-transform, it is down to 10 kilometer depth. Should be reversed. Along the tectonic part, it should be deeper and shallower. So one of the idea we are developing, and then I got this idea. How do I go back? Anyway, so this was a contradiction. So I said, well, it's possible that it could be due to the melt present, which is moving and reproducing it. Then I talked to Bob White, who is in Cambridge. He said, well, it could be CO2. And that led us to hunt for CO2. So our colleagues have been looking at the petrology of the rocks. And this is the barium composition of the basalt, and this is neodymium, rubidium, and ratio of potassium and titanium. And you will see that this is the curve of presence of CO2 with the amount of barium, and this is where we are. In our case, means that about 2.2 to 4.5% of CO2 will be required. Similarly, neodymium is giving the same response, same with the rubidium and potassium. In other words, you could have a large amount of CO2 coming out of solution and producing those earthquakes. So this is the cartoon we are preparing, saying that this seismicity is linked to the dissolution of or degassing of the CO2 from the melt and producing the earthquakes. So it has two implications. One is that the part of the melt we are seeing beneath the lab could be due to the presence of CO2 as well. So we could have a lot more melt than we had earlier realized. So conclude what we have discovered, that lab is age-dependent and underlain by melt silts or lab channel. We need about 1.1% of melt to produce the reflections, but as we are discovering, could be larger. We do not know how thick is that melt lens, because using seismic reflection technique, all I can resolve is it is 500 to a kilometer. I can't say more than that. One of the idea is that melt is entering beneath the ridge axis and get trapped underneath the lab, and in the lithosphere, when it freezes, produces the heterogeneity. And so the mantle lithosphere could be much more heterogeneous than we think. And we also discussed the lab is thin beneath the transform faults. Presence of melt beneath the lithosphere will decrease the viscosity, and hence the plate tectonics will not depend on the mantle convection, but other processes. And I've been discussing with Carlo, there could be other processes apart from the plate subduction pull and the ridge axis. And the melt channel could be responsible for leaky transform pulse, and melt can travel very far distance beneath the lab. So that concludes my talk. I would like to thank ERC for funding this project. Without that, we'll not have got this project funded. German Science Foundation funded the ship time for one of the experiment, and Schlumberger donated a large chunk of money for doing this survey. Thank you very much for your attention, and happy to address questions.
Excellent. Many thanks, Satish. It was a very inspiring talk. Are there questions from the audience? Andrea, please go ahead.
Thank you. Hello, Satish. This is Andrea Morelli. Nice to see you. Sorry I could not be in Rome. I have a very nice presentation. Thank you. I was wondering, could we be looking at a local feature, or it would be safe enough to extend this to the global scale? I'm referring mainly to the LAB Gutenberg duality.
Yeah, so the results we are showing is from 2 million to 74 million years. So it is global enough in the Atlantic Ocean. It is not by accident we discover. So it can happen that it's a fluke we found. But if you think about it, it's a general feature. I'm more confident about Gutenberg and the lab. So if you're asking me, do I believe the distinct boundary between the two? Yes, and they reflect the broader, because everyone uses surface waves or scattering on a very small scale. Here we are looking at 75 million years. That answers your question, Adrian?
Yes, thank you.
I have another question, Satish, about the temperature at the lab, because I know the Cambridge model of 1250 degrees for the lithosphere-asthenospheric boundary, but going down, we know that it increases the pressure. So we would expect that the transition with solid and partial melting should increase also temperature.
Yeah, so here we have taken the pressure into account. So what will happen, I think in the paper Maharshi and Singh we talk about, so temperature remains more or less similar, but the water content changes. So water content in that paper we discussed, which I do not discuss here, becomes higher concentrated. So the temperatures remain similar, whereas water increases. So for older ages, because assuming that's a lab channel, as we freeze the solid, water goes into the liquid, not in the solid. And older it gets, dense, more water in the melt remains. So in that paper I did not discuss, we suggest that amount of water remains more or less constant with age, but the concentration increases with age, and hence the temperature remains constant, more or less. But again, this isotherms are approximative. I will not put my neck out to be chopped off if you're asking.
Thank you. Other questions from the colleagues? Well, you were talking about a possible decoupling. We know that the ridges are moving. So I wonder how this model would apply with a dynamic system, with the ridge moving.
So if the ridge is moving, there will be some asymmetry. So only thing I see, the basic concept will not change. The 1250 is approximate temperature. Again, it will be 20 degree plus minus. That's the first thing. Will this symmetric of the ridge axis? I'm not sure. There will be some asymmetry in the deep of the lab. And in fact, I did not show. We are writing another paper west of the Atlantic. This area we are studying, the situation is more complex. Other thing I didn't mention, which is important, our colleague in Southampton suggested that the lab could be undulating, and due to small scale convection in the, we find that the geology controls more than the small scale convection. In other words, if there are small scale features like transform faults or extension afterwards, the lab will change accordingly. So ridge moving is part of the geology for me.
Excellent. Any other question from the connected colleagues? If not, well, we can close, and thanks again, Professor Satish. So thank you everybody for coming, and see you next time. Bye.